So let's do this one thing. We'll send a message. But then yeah, we will make it. I wish it was. I really wish it
That sounds like
was. Really need one.
I saw them up. You guys are doing honestly, you know.
Yes, two talks, discussion and
So let's wait a couple of minutes that people get in here, and then we'll start the session.
Wait, sorry, I don't know. Who's. No worries. First one is off.
Whenever you're ready, just make sure that it's a big green, like, just turn it on. You just have to press that button. I think we can begin.
Just push that.
Yeah. Can you see? Hello.
Testing.
Yeah. Perfect. Do you want to take over or do you want me to?
Oh, good. I'm here.
Okay.
Hey, Namisha.
Well, how could I miss you?
Aw.
Sorry. Hi, everyone. Welcome back. I hope you had coffee and now you are energized after the first session. So our next speaker is Asa. He's going to talk about galaxy quenching at the high redshift frontier. So to you, Asa.
Great, thanks, Namisha. I think I have the mic. Hi, everyone. I'm Asa Block. I'm a professor at FIU in Miami, and I'm delighted to be here. Huge thank you to the organizers for a fabulous conference and for all of you to sticking it out to very near the end. So today I want to talk about something that I know many people in the room are interested in, the transition of galaxies from actively star-forming systems to systems that are no longer forming stars in a process that we often refer to as quenching. And, just a bit of trivia that I'm sure many of you are already aware of, the supermassive black hole in M87, which is kind of the poster child for a quiescent object, contains the first supermassive black holes that humans ever had an image of. And I believe that's not an accident at all. So I want to start by just kind of thinking about the problem in the biggest sense. So, we often think of galaxies as being something big, but they're surrounded by something much larger. They're halos, which are full of baryons, typically. So we have a galaxy at the center where all the stars are, surrounded by a halo full of dark matter and baryons. And of course, as I like to say, no halo is an island. It's connected to the rest of the universe, and gas and dark matter is flowing into it. The baryons can shock heat as they enter into the halo. We can have circulation of gas through stellar winds and supernovae. And then we can have various forms of AGM feedback from relativistic jets and also from thermally ignited winds, among other possibilities. But here's the issue. Only around 5 to 10% of baryons end up residing in the small, wet, cold puddle of a galaxy at the center, even though simple models suggest that it should be closer to 100%. Most of the baryons in a high-mass galaxy, over 90% of them in many cases, reside out here. And the issue is that they're in an approximately 30 million Kelvin plasma in a 3 Kelvin universe. So the second law of thermodynamics tells us they should cool down. We can work out the cooling rates, and it is short enough that we would have expected these things to have collapsed were it not for the complex interplay of these feedback processes. Another way of thinking about this is that if you plot the number density of galaxies expected from just pure baryons being formed into stars, you get something like this power law. But then, as we've seen many times before in this conference, the reality is quite different. And so theorists plug the gap in 2 ways, with supernova feedback at the low mass end and AGM feedback at the high mass end. But I'd like to look for the observational evidence for this and also think about the best methods to test these paradigms and make sure we're on the right track. So just to summarize, there's 3 interconnected big picture questions related to quenching. The first is, why is star formation so inefficient? Why does only 5 to 10% of baryons ever make it into stars? Why is the hot gas halo stable to cooling can collapse if there's not a heating source? This is the most flagrant violation of the second law that we've ever found. And finally, why is the galaxy population bimodal? Why is this diversity in star formation column, morphology, and structure existing in large galaxy surveys? So to begin to look at this, we started off by collating at the time 3 of the largest and most sophisticated hydrodynamical simulations, Eagle, Illustris, and TNG. And from these, they all utilize AGN in a strategic way to enable quenching, but they have different modes. So in Eagle, they have a single mode through stochastic heating, somewhat like a quasar mode. In Illustris, there is a quasar mode with an additional radio mode. And in TNG, the radio mode is replaced with a kinetic feedback mode. And these will give us some theoretical predictions of what we might expect to see in the galaxy population from AGM feedback. And to start with, at least, we wanted to compare this with the largest spectroscopic survey of galaxies in existence. I believe this is still the case today, Sloan Digital Sky Survey, and of course, many people have contributed to this over many years. So a simple idea was, if we accept we need a heating source, which I think we should, then here are 3 ideas. 1, the heating could come from supermassive black holes. 1, it could come from virial shocks, and 1, it could come from supernovae. And then it doesn't require a huge amount of work to realize that this is then just a straightforward classification problem. We have some input variables or features. We can measure them in a variety of different ways. We can pass it through a classification algorithm. We chose to use random forests because they're particularly powerful at separating causal from non-causal variables. In fact, I'm very excited by their potential beyond this study. So here's a paper I wrote specifically on the methodology. And then we separated it out into 2 classes, quenched or star forming. And the neat thing about random forests is that you can work out exactly how important each feature was at each step. And so it really isn't a black box. This is one of the really nice aspects of this type of machine learning. And so when we do it, and this plot was already showed today, but I'm grateful for that, I'm happy to show it again, we found that in all 3 of the simulations, black hole mass dwarfs the other parameters. It's absolutely clear that in the simulations, you should find black hole mass to be the best predictor of when a galaxy is quenched or star forming. And this is true regardless of the feedback mechanism. And this is really interesting because it points towards a general truth about this class of models. It's a paradigmatic test rather than a specific test of a specific implementation. Then we tested in the SDSS with approximately 400,000 central galaxies using 5 different calibrations, using a variety of methods, including central velocity dispersion, bulge mass, and so on. And we find exactly what was predicted in the model. So we think this is really strong evidence for AGM feedback impacting the local galactic population. And for a much smaller sample of 100 dynamically measured black hole masses or so, we also find perfectly consistent results with the calibration study, all in agreement with the paradigm. One other thing I want to point out before we move on to the high redshift aspect of my talk is that another possibility, and it's a very common one, is you might want to test the AGM feedback effect on galaxies by looking at AGM. And this plot shows why this is challenging. Here I'm plotting accretion rate, which is obviously the source of AGN luminosity, and what you see is black hole mass, which is strongly correlated with the integrated accretion energy, dwarfs the power from the current activity, and in fact is comparable in strength to these other physical processes like shocks and supernovae, and not much better than random. And this is important because it impacts how we as observers need to test these theoretical models, even these relatively well-established ones. So I can put it in even more observer language. On the bottom here, I'm plotting the black hole mass distributions from these simulations in beautiful work done by my student, Joanna Piotrowska, who was a student of mine at Cambridge and now is a postdoc at Caltech. And what she found is that there's this very clear offset in black hole mass, and that's great if you want to separate the populations and understand what's going on. On the other hand, if we look at the total bolometric AGN luminosity, these simulations predict much less of a difference, and they also disagree with each other as to whether the difference should be positive or negative. So simply finding high luminosity AGN in star-forming galaxies, or low luminosity AGN in star-forming galaxies, in fact you can find whatever you want depending on the specific implementation, and always the results are subtle. Whereas if you look at the integrated history, the results are really super clear. And I think that this is perhaps the most important takeaway I have. Moving forwards, so now it doesn't play, okay. Oops. Okay, there we go. So you can't come to SCSCI, and it's my first visit, so I want to be invited back, without talking about the phenomenal observatories that, of course, you provide for our community. And we've extended this phenomenal work by my student out to the high redshift frontier using HST candles and JWST seers. So in the final few minutes of my talk, I just want to show you how we were able to extend it and what we found. So the first thing we needed to do was extend the predictions from simulations to cosmic noon and beyond, and we abandoned Illustris for this, because the first takeaway is they don't produce quiescent galaxies beyond around redshift of 2. So then that left us with Eagle and TNG that we were currently working with, and we find exactly the same characteristic at cosmic noon and beyond as we found in the early universe. We find that they predict black hole mass to be the dominant parameter, still not accretion rate, and none of these photometric parameters. But these are hard things to measure, especially in the high redshift universe. So what we looked at was a photometric friendly projection of this parameter space, where we select the parameters that we can measure relatively well in photometric surveys, both in from HST and JWST. And what we find is if we limit the simulations to this parameter space, they predict that the stellar potential, essentially the ratio of stellar mass to stellar size, would look like the dominant quenching parameter in lieu of a measurement of black hole mass. So this gave us something that we could go out and we could test and we could do immediately. Rather like how we've used proxies for some of our studies at redshift 0, like central velocity dispersion. But of course, to get central stellar velocity dispersion, you need large spectroscopic surveys, which don't currently exist at these redshifts. So the main takeaway is these simulations do make a prediction in this A causal parameter space that black hole quenching should look like stellar potential quenching. And here's a brief argument for why it kind of makes sense. Great, so this is something we can test. Okay, and if we go out and some reason, oh, there we go. If we go out and test it, first of all, we have to define what a quenched galaxy is across cosmic time. And a quenched galaxy is something that lies below either the green or the red line. We tried both. This is the inverse Hubble time, and this is a third of the inverse Hubble time. And we see these do pretty well against the lower end of the evolution in the SSFR sequence. And when we test it, we find something that I think is quite remarkable. That all the way from redshift 0 out to redshift 4, and combining 3 of the largest and most wonderful galaxy surveys, STSS, CANDLES, and SEERS, using JWST, HST, and the STSS telescope, we find this remarkable stability across cosmic time, where galaxy quenching depends on the stellar potential as predicted in the AGM feedback model. And we also went and tested this in the SDSS with the spectroscopic parameters, and phi beats everything apart from central velocity dispersion or black hole mass that we could throw at it. Now, I'm going to have a beep in a minute, so I'll skip this one, and I'll just show you this. You know, observers love plots like this to really kind of look at the data. So here we're plotting the stellar potential against stellar mass, and there's meaningful variation in this direction due to varying the size. I'll just take 30 more seconds, and you can see that these quiescent galaxies cluster at this top end here at redshifts 2 to 4, and even in the extraordinarily early universe, those few quiescent galaxies that we found and we believe to be real are all clustered in this same parameter space, which is to say that they have the deepest potentials out of any galaxies at any epoch, obviously the natural environment for supermassive black holes to grow in. This is just showing you the same result in another way and some more statistics, but we don't need to dwell on it. And then I will leave you with my conclusions. Thank you for listening.
Thank you, Asa, for the talk. What questions do we have for Asa?
Yeah, okay. So observationally, if you're going to look for these signatures, so at least in redshift 3 to 5, we see not all galaxies have AGN signatures, right? So if I understood correctly, looking into these potential is an independent measure of whether there's a black hole, independent of whether it's like accreting or not. Is that correct? Okay.
Yeah, so absolutely that's correct. I mean, you know, so I'm in an AGN session, and I care about AGM feedback, but I often say I study AGM feedback without studying AGN. And the reason for that is the stochasticity is such that because we are in AGN now doesn't mean you weren't in the past, and vice versa. And so what I'm looking for is a tracer of the integrated history, and the reason I'm looking for that is it's because what models predict will really show a signature in the data. And so, you know, that has led me from studying AGN to studying the fossil record of AGN.
Hi, really nice talk. So I was wondering about sigma. Like, did you measure velocity dispersion from the central region, and do you see, since you saw this like expected?
Yeah, so I didn't personally measure them, but they're provided for many of these surveys, particularly in the local universe from the SDSS. So yes, we use central velocity dispersion, and it is the best predictor here at the redshift 0 bin. It even beats phi, and I think it makes sense. And my argument for why we started looking at phi is it's supposed to correlate very well with sigma, and they're both supposed to correlate with black hole mass. The reason we don't do it here is we just do not have the sample sizes to use them in a meaningful sense yet. But one thing that's coming and that I'm super excited about is VOT Moonrise, and they will provide, hopefully, of the order 100,000 spectra that will be good enough to get central velocity measurements. And this is something that will be a real game changer for this kind of fossil study that I want to do.
Hi, a very nice talk. So in our observational study, we found that sigma was less important than stellar mass to decide the radio AGN activity of a galaxy. I mean, I'm not too sure if these two are conflicting things, or might they agree in some space? Thank you.
Yeah, so the question was, you know, in your study, which I obviously need to read, you find sigma is less predictive of radioactivity. But for sure, sigma is extraordinarily well predictive at quenching. So one possibility is the type of historic feedback that's important is not radio. I happen to suspect that it might well be radio. So then there's also an effect of the current radioactivity and the history of radioactivity are two very different things. And then another possibility is what low-level jets exist below the threshold. And the thing I always want to emphasize with my approach is when you care about doing something to the halo, you care about the work done to the halo, which of course is a type of energy, and that's a power times the dt. So what I think some approaches miss, I don't know, I need to read your paper, but what some approaches can miss is the importance of dt. There's more than one way to provide a certain amount of workload to balance the CGM. One is to be very powerful for a short amount of time, and the other is to be very weak for a very long amount of time. And so one possibility, and I actually think it's likely, is that this works so well because the delta T may win over the luminosity in many cases.
Okay, thank you.
Great. Thank you, Asa. Let's move on to the next talk now.
Thank you.
So our next speaker is Vincenzo Di Onofrio, and he's going to talk about quenching via tidal removal of cold gas from intermediate redshift massive post-starburst galaxies.
Thank you so much. Oh, already revealed my conclusion slide. It's all right. Spoiler. Yeah, so I believe in the last talk today, I'm Vinny. I'm a second-year graduate student at Texas A&M. And today, as the last talk, I'll deviate from this session, only briefly from AGN feedback stuff, but then I'll also deviate from a lot of the traditional mechanisms that we've been talking about for star formation regulation. And so we talked about my work, qualitative new quenching mechanism, tidal removal, cold molecular gas in higher, right, 0.7 redshift post-starburst galaxies. And this is work I've been doing at TAMU with these lovely folks at Squiggle. And so, right, we've been introduced to many of the various processes, a lot of the supernova and AGN-driven outflows, a lot of the environmental effects. But today I'll talk about why these processes don't need to be the only mechanisms required for the regulation of star formation. And so I'll be talking about my, I can do this with Squiggle, which stands for studying quenching in intermediate galaxies gas. Yes, L does stand for angular momentum. Evolution. Acronyms in astronomy, but take it as it is, right? And so Squiggle basically has a paired sample of sort of 1,000 galaxies. These recently quenched massive, what are called post-starburst galaxies. Right, we discussed a little bit of them throughout this week. Squiggle offers multi-wavelength analysis of these objects to kind of probe the quenching process. Awesome. Sorry about that. Yeah, and so first I'll be showing this new mechanism by detecting some of the molecular gas spectroscopy that we get from Squiggle. And so, right, post-starburst has been mentioned kind of briefly throughout the week. Just to give a little bit of overview, right? It's kind of our. I'm sorry to break you. Sorry. Oh, how much to turn off? Thank you. Okay, yeah. That was my one job, and I failed. Okay, sorry about that. Yep, so yeah, post-starburst galaxies they're caught in the transition between our two main types here, right? As the name kind of says, right, they kind of undergo a recent burst of star formation that's rapidly quenched and eventually depletes, depletes to a very low SFRs, right? They have right? Their spectra are very different from the other two types. They're dominated by their Balmer line absorption, indicative of these intermediate aged A stars. And they're perfect kind of clocks for quenching. They're able to really probe right, this transitional stage. And then, more importantly though, is why are we using these higher redshift PSBs? Why can't we just use our sample or samples from the local universe? That's because if you look here and look at kind of their older star, right, their redder contribution, comparing our Z of 0.7 to Z of 0 spectra here, we see that the local samples have much more of an older star contribution. And so, after they go through their kind of starburst phase, only roughly 5 to 10% of their total stellar mass fraction is actually comprising of these recently formed stars. Whereas the black line here, we see that a much higher population, twiddle 70% of the squiggle PSBs will be dominated by this recently quenched event. And so, we're actually able to, with these higher redshift PSBs from squiggle, we're actually able to probe in these galaxies, much of these recently formed stars. And so I'll build up some of the previous results and groundwork from squiggle. And so right on the left here, we have all of our objects twiddle 50. We have ALMA deep CO 2-to-1 measurements of, and kind of the interesting thing that we see here is that we see for majority of detections, we're comparing to our, just on our KS relation to our normal galaxies, we see that the CO detected PSBs are much more gas rich than normal star-forming galaxies. And so these would suggest that while these galaxies have recently quenched, they still possess these massive reservoirs of molecular gas. And so kind of indicates that they're inefficiently forming stars. Why? And so one of the other key results from squiggle is that we can compare the gas mass to the time since quenching. And so we have this question of how is this gas being removed? Is it being removed rapidly? And so we can see here on the left here and color coded in the blue kind of background shading, we can see that all the CO detected the gas is only detected in the youngest kind of PSBs here. And so there's something that once the galaxies post-quenching reach a certain age, something needs to be driving out that gas. And so in this study, I'll be talking about kind of two pet rocks that I've been working with for the past couple years that kind of shows some of the most unusual gas properties in the entire squiggle sample. And so first, I'll show the just our WIPC3 images, or direct images from Hubble, and we could first notice these stellar tidal features indicative of a post-merger. And in fact, later in the merger stage, right, we don't see an obvious evidence of any dual nuclei or anything showing maybe an earlier merger phase, right? We just see these prominent late stage feature tidal tails, and then I can overlay the integrated ALMA CO contours onto it, and we can see that a lot of the gas, we have these gas in these, a lot of the gas has been displaced in these very extended features. We can see in this one, the gas nearly perfectly aligns with our stellar features. This one, not so much. It just kind of goes to show that, right, this space is very limitedly sampled, but we only have two objects. We're obviously not spanning the entire sample space, but we do see that about half the gas in each galaxy has been displaced, which you can't get from just ionized outflows or anything which only maybe will comprise of 10% of the gas in our extended regions here. And so we just have these two objects with just massive reservoirs of molecular gas at these extended regions. But we also have for recently quenched galaxies huge reservoirs of molecular gas in the central regions. And also you might be wondering, we've been seeing these mergers with these tidal features that have some amount of gas since maybe the 90s. And so this plot here just shows that these galaxies are extreme in both magnitude, right? The magnitude, the actual amount of gas is in the tails, and also the extent compared to what I have plotted here in the background. Any merger across cosmic time, these galaxies are extreme in both of these molecular gas properties. right? And so, we have this picture of this gas has been displaced, but what does that mean? What does that imply for the star forming properties? And so we got HST GRISM data, which GRISM 102, which covers the our H alpha star forming tracer. And we can see something quite interesting here in this one galaxy 1448, where we see this clump of H alpha, which we think which we have a great indication that this is just ionized from a central AGN. And then we have these H alpha clumps along this prominent northern tail in this galaxy. But we also have very high sigma peaks, kind of in these two clumps here. For the other galaxy, it's just just in the central. And so if I plot these points on our KS relation, we can see something quite interesting, right? The central galaxy here, these are just STD points, again, because we think that this is largely AGN. But the central, the tidal regions kind of sit above, these points here. They're behaving more as normal star-forming galaxies. And so kind of the thought is, a lot of this gas has been dispersed into these tails. The central galaxy is not forming any more stars, but maybe some of that star formation has been displaced to these extended regions. Right? We can also see how well aligned these two H alpha hubs correspond to the molecular gas. And so I talked a little bit about this first, this initial quenching stage, the tidal removal of molecular gas from these galaxies. Also, I'll tie back in the AGN feedback a little bit and show, these galaxies have been initially quenched, but what is keeping the star formation rates low in these galaxies, as we see, and thinking back to that gas mass versus time since quenching plot, what is driving out the gas eventually of those older post-starburst galaxies. Right, and so we have great reviews of a lot of the radio mode versus quasar mode feedback. So again, as I laid out, we think the initial picture is this tidal removal of cold molecular gas from these galaxies, but then the star formation is being, suppression is being maintained due to this radio mode feedback. And so we want to kind of tease out some of the properties of AGN in our galaxies. We first have some 6 gigahertz data from VLA, and in our one here, we see which also has these broad emission lines. We can see kind of this nice double load, kind of like maybe young radial jet structure here. And then in the other one, 2258, I don't have the beams on here, but it's fairly compact, but it's just low, faint emission. So it's not obviously not indicative of any AGN activity. We also have NIRES detections of 13 of these post-starburst galaxies, and then we can combine that with our coverage from SCSSS, make our BPT, and we have this galaxy on the left. It's clearly an AGN region. Unfortunately, the only galaxy that is not classified in AGN from the classical BPT is this other galaxy on the right. And so kind of our final conclusions on what is currently going on in the galaxy, or in terms of the AGN feedback, we have strong AGN in 1448. We can't really say much about the other galaxy. And so, this whole novel view of radio mode feedback is not complete. Right? We're only looking at 2 galaxies, and we have total 50 objects that we can look at these, and we can tease out some of the timescales and mechanisms for quenching in galaxies. And so, looking at, I'll take you back to this kind of relation here. Now we're color coded are the CO detections. We're also, in the y-axis now, we have the VLA flux. And we can also see it's very preliminary, but we can see that the VLA detections are mostly in the youngest squiggle PSBs, which actually kind of corresponds with the previous squiggle result from Jenny Green, which basically shows that when we're the optical nuclear activity, when we're just selecting potential AGN from just our O3 H beta ratio. We also see kind of this ratio, or this relation here, where the fraction of AGN is 10 times higher in kind of our youngest spectral age regions, and kind of depletes as we go out. And so, I'll leave you here this time, just talking about this new, qualitatively new mechanism for quenching, and thank you.
Thanks, Vincenzo. What questions do we have?
Thank you. Very interesting. So my question is, despite the removal of gas in the tidal tails and maybe the AGN at the center, so my question is, there is still a lot of molecular gas at the center. So how is that it's not forming stars? Is it not like dense enough? Is it warm?
Yeah, so kind of the thought is, right, from just radio mode feedback, we're thinking that, right, if these galaxies do have AGN, it's just heating the ISM, right? It's not allowing for the conditions for stars to collapse back or get cold enough again to form again. Right, yeah, right. It's a good point. Right, we still have the 50% of the gas is still in the central galaxy, but it's not forming stars, and so there's got to be something going on. It's just not letting that cold gas to just get back to those star forming properties. And we think that's the radio mode feedback.
Great talk. I was just wondering, do you have any information to potentially spatially resolve the post-starburst features within these post-starburst galaxies and potentially link the kind of
just like resolving
resolving it to, and then comparing that to where you're seeing H alpha in the radio, because it's interesting that you have the kind of radio emission at the center and then these H alpha emission as well for identified post-starburst galaxies, but it'd be interesting to see if you can see these features like in a spatially resolved sense and try and connect where, like for example, is that central post-starburst or is it kind of ring structure? Is it quenching going inside out or outside in? Is there any plans to potentially go down that route? Or
a lot of our plans are to test the central galaxy, right? And just testing any of the our future observations or just testing the AGN there. We want to know like what's maintaining this decompression. So yeah, like I don't know, maybe I'm misinterpreting this, but like kind of an initial thought was like maybe, and again this is probably going on a limb here, but maybe some of these stellar H alpha hubs could be maybe progenitors to some kind of like a TDG or something, which is kind of a very like early discussion that we had, but yeah, in terms of we don't really have too much plans in that direction.
Okay, thank you.
Well, so that was the last talk of the symposium. So let's thank all the speakers. And now we have the discussion, which will be led by Katie Alatala.
I'm gonna be able to use this. So, I need to get set up, and I called for the assistance of Giovanni and Danielle to run this because this is the last discussion of a 5-day meeting. So I was not certain that everybody would want to sit and be non-interactive, and so I'm gonna do art. So let me give this to either Danielle or Giovanni. But what I'm going to do is turn on my iPad, and we're going to be drawing some AGN for our discussion section today. And it's going to be interactive, so people will get to raise their hands and tell us things that we need to add to it. And I believe that we're going to do it on WebEx so that everybody online can also participate in this particularly fun experiment. There. Oh, no. Okay. Almost gave me the magic password to get me to our meeting. All right. I think I just connected audio and that's bad. All right. Hopefully, are we good? Give me a thumbs up if we're good. All right. I have an Apple Pencil. Let's draw our first AGN, and then we're going to have people start to talk about things. And I practiced only a little bit because I figured this was either going to be fun to be like, wow, Katie's art is great, or it's just going to be funny. We're tired. So here's a black hole. Here's a galaxy. And here's the CGM. Okay, so we're going to start with this. Not to scale. No, no, no. Oh my gosh. My mother would be so sad seeing her librarian daughter handwriting like this, but here we go. Okay, so what I need to know now from the audience is, now that we have sort of the schematic here, what are some things that we should probably put on here? Things like gas flows. I think I can point out Freke had an incredible cheat sheet for this, for anybody who wants to think about gas flows and what they're going to look like. What are the things that the AGN is doing that impacts star formation at the CGM level? So at kind of the big, broad, stopping star formation completely. So feel free to raise your hands. Giovanni or Danielle can also shout some things out, and I will attempt to draw them. There we have jets. But they're obviously bipolar. There we go.
Can we add the IGM, please?
We're going to test how well I do. Let's see. Okay. I can put radiolobes on there. So here's the question. For the CGM, IGM scale radiolobes, are we thinking the little ones or are we thinking the big ones? So is it that? Or is it the ones that when we get to it, I will draw another thing, and it's going to be how the AGN impacts star formation just in the galaxy. So this is the big scale thing. We're going to see how I do when I draw the small scale thing too.
So maybe related to the radiolobe. So what kind of jet are we thinking about? We've seen examples of like smaller jets that may be pointing towards the ISM, or the larger scale jets that might be injecting energy onto the CGM or even beyond. Do we need jets that are precessing somehow so that they distribute the energy in all directions?
I think you probably want several episodes of jets, because we've got things falling in that are triggering starbursts and jet events, different ages.
We also have infall. My goodness. And different episodes of jets. Although, as we know, a jet does not necessarily always have to be in the same axis, so it could be a case that the jets are precessing. So we could have some on this axis, but then we could have other sort of events over here, like that. I try to draw this. There we go. So this is a past event.
So is it just radio jets that are doing this work, or also winds in other forms can inject energy in the CGM and do the same job or not? I don't know. Question.
So where should I draw the winds is the question. So for anyone who did not hear that online, the answer was everywhere. Oh.
Redshift.
I will point out, we actually talked about this. So we're doing low redshift.
That's why the space on the right.
Environment. So, my goodness. One problem with the WebEx is it does not recognize my palm and the Apple Pencil as separate, like a lot of programs do. So that's making it even more fun. Is the point of this section.
So going back to winds, maybe, on what scales do we expect AGN winds to have an impact on star formation? This kind of diagram. Is it just opening up a cavity in the center of the galaxy? Is it like helping to heat up the CGM?
I think, something we see even in nearby C4 galaxies is, ionized outflows, few thousand kilometers a second, but generally only reaching, hundreds of parsecs, maybe a kiloparsec or two. But the deeper we go, we still see ionized gas that's maybe still rotating but hot and turbulent out to, tens of kiloparsec scales. You don't necessarily have to clear the gas out, you just have to keep it hot. And so I think that's kind of a nice bridge between scales in this picture.
Nice, thank you. Yes, we have.
We can also have, is this on? Yes. We can also have like X-ray bubbles and Fermi bubbles, like as we observe in the Milky Way, right? So like CGM, whatever, outside the galaxy.
Great, thank you. So do we envision that created by like a small jet or by winds, by what could be the driving mechanism? All of that? Okay.
Zooming in now. No, just zooming in the galaxy.
Wow. I'm going to say, now that we have covered this in my handwriting and beautiful art, let's zoom into the galaxy and ask the same question, which is, what are things that suppress or cease star formation on closer to sort of the kiloparsec inside the galaxy scale? And let's draw some of those things too. I'll even draw a little gas disk for people in the nucleus. Well, if no one's going to say anything, I'll say the radio jet does plenty of work even there. And in the nuclei, the radio jet doesn't have to be anywhere near as powerful to have a pretty substantial impact. So the radio jet does a lot of great work on the CGM scale. It also does a lot of great work sort of very close to the center.
So what do we think in terms of galaxy like kiloparsec scales, in star-forming galaxies, who do we think wins in terms of like impacting directly the ISM? Jets or like wider angle winds? Any strong opinions?
So I'm only moderately completely biased in this perspective, but I think the wider angle wins in the low redshift universe in particular, because they have a much larger opening angle. You're ionizing a huge amount of material, and at least in a handful of the lower luminosity systems, we see this kind of extended radio structure, but it's not entirely clear if it's really a jet that is driving and ionizing the gas, or the ionized gas is driving out and clearing a cavity, allowing the radio emission to move through. Of course, at high redshift, that's a very, very different story. But I think if you had to say in general, I would lean on the side of ionized winds over radio.
Great, thank you. Other opinions? Yeah, over here.
In TNG, at least, it seems to be the heating mode from the feedback, or from the AGN feedback, that's really driving quenching over the kinetic mode at low accretion rates. So
First and foremost, I think we need to acknowledge the ionizing feedback that you get from an AGN that's not mechanical, it's radiative. And so if you're pumping a whole bunch of ionizing photons into your gas and heating it through photonization, that's going to make it really hard to form stars. So that's a huge caveat. The other caveat is that an AGN don't spend all of their lifetime in the radio mode. They spend a lot of their time in the more like radiative kinetic mode, where they are predominantly doing these sort of wide opening angle winds, and they are pumping out a lot of ionizing photons because they have these higher accretion rates. And so I think understanding which like galaxy mass regimes might matter, even at low redshift.
That's an extremely good point. So are we happy with this wonderful picture and this beautiful art for AGN feedback and how it works with star formation, cessation, and suppression in the local universe? If we are, I will say that I am absolutely going to save this and let everybody have a wonderful copy of it. So is there anything missing? I would also say, not just in the CGM picture, which the environment, if it's a brightest cluster galaxy, you're going to have cluster gas that is preventing is creating cooling flows, but those cooling flows are not bringing enough gas to make these ultra-massive galaxies that we were expecting. But also, obviously, at the galaxy, the single galaxy scale, being in a compact group, for instance, means that, number one, all of these gravitational torques are going to be driving more gas into the AGN, but those gravitational torques could also be impacting the star forming, the ability for the star forming disk to actually form stars.
I think that we're also missing something, like it was mentioned, but there's all the theories of like linking different AGN winds from the accretion disk and the nuclear scales to the kiloparsec scales. So like UV winds, C4, for example, or X-ray winds, how they then convert or they drive or they don't drive the kiloparsec scale winds. And in case it's not the nuclear winds, then how are the kiloparsec scale winds driven?
Great, and maybe related to this, are the inner winds like energy conserving, and do we have like a momentum boost with energy conserving winds, or are they are they cooling efficiently and therefore only maybe momentum driven?
We're attempting to have other scales. My fine motor control is going to be the limitation of how many scales we can draw for this.
And how does that affect, how does AGN affect dwarf galaxies and accretion of gas into these satellites?
So how does the AGN impact the accretion of gas into, the AGN in the central impact the accretion of gas into the satellites? Yeah, that's a really good one. I'm not entirely sure how to draw that.
Does anybody want to answer that? How do
Maybe
AGN?
I'll put a little sad face on it. I'll make a little galaxy and put a sad face on it because the AGN is not letting it form stars. Everyone just wants to see me draw a sad-faced galaxy, I'm sure.
So I guess tying into our theme of the conference here, one thing we could add to our mid-scale is our little H2 regions. And so something that I still always struggle with is, we're building this picture of feeding and feedback, but how do we really accurately measure star formation rates when we have all of this, AGN contamination? A lot of our emission line diagnostics are contaminated, H-alpha, O2, radio, pretty much everything. And so how do we really robustly measure, radial star formation rates in these galaxies where we have so much activity going on?
Also talking about dwarf galaxies, specifically satellites, it depends on where they are at, like located in the disk, because if AGN are carving out these cavities, then ram pressure stripping is going to affect them less. And so you're going to have different star formation rates depending on where it is.
So if I draw, so maybe a little galaxy in a lobe that has a smiley face, because it's still actually okay in forming its stars.
So I would actually argue that you should draw the trajectory of the satellite through the CGM, because its orbit and its orbital history will depend on what it's been encountering along its history.
That's a really good point.
Great. So I guess we've seen beautiful results on the how satellite galaxies are like round pressure strips, both in simulations and also in observations. So going back to AGN feedback, is there any evidence, either from observations or simulations, on what would be the impact of AGN feedback? Or could that like enhance the stripping in satellites?
I'm not an expert, but during one of the breaks, I was asking Chris Carr kind of about this, and he said that there was some level of observational evidence that indicated that dwarf galaxies might be more star forming in these cavities because the ram pressure is less. And then we actually know that there is some evidence that a small amount of ram pressure stripping can induce star formation in these smaller galaxies as they're kind of like infalling into a host.
So I put the little smiley face guy with their trajectory where it would be forming stars a little bit better.
Wonderful.
Hi, Katie. One of the things I'm seeing missing from this picture is one of your favorite things, which is actually molecular outflows, which is what you saw in NGC 1266 and was a prime example for how outflows can stop, star formation. So maybe you want a little molecular outflow bubble there.
I think I'm going to put it in the galaxy scale, but yes, molecular outflows in the local universe do help deplete the gas. They also inject turbulence into the existing star-forming fuel, and by injecting turbulence, it actually makes it harder for the gas to gravitationally collapse and form stars. So let's see. This is getting very complex. I'm really happy that my idea to have a little art session at the end of the conference is working so well too. So thank you all for participating with me.
I think it's demonstrating why we don't understand AGN feedback. It's just a mess.
This too.
So what about with molecular outflows? What about accelerating is it acceleration of like molecular clouds from the ASM somehow like surviving to like 1,000 kilometers per second, or is it a formation of molecules in situ?
What I've heard from people, the theorists and simulators, is that they simulate both scenarios, but one of them is with the strongest evidence, and we've seen spectral signatures, very preliminary work that looks very much like what an expanding bubble, expanding shell of and the molecules are forming on the outer part of that. So we saw spectral signatures with mirror data that look like that. So maybe that is something that, like expanding spherical structure and the molecules forming outside, not being driven from the accretion disk region. So.
Okay, thank you. Any other strong opinions about?
I would just say, like, I don't know whether we discussed this right now or not, but it's one of the few conferences where I've not seen an AGN torus structure so far. We did have an AGN session, so I don't know, where does torus fit into this? I think you'll have to really zoom in over there
I think it would be in the torus, I guess, would be on the outskirts of the zoom in. So here. Trying to draw my torus so that I don't cover things that I've written. There we go. So that's where the torus would be. It's true. I guess I have just artistically rendered a clumpy torus. It's a patchy torus.
This is really great. Thank you. Thank you.
Yeah,
Kate,
I
for
was gonna
this.
say. I think we're a little bit over time. Is there anything else we need to add to this beautiful picture?
What I was thinking, I actually, I don't know if you have already mentioned this, like, but since this is like in the end is an overall picture of what we discussed this week, like the chemical, like the effect of the Asian feedback on the metallicity and on the chemical content of the galaxies. So, you know, we see that outflows can be more metal rich than the ISM in the surroundings. There are some evidence in that direction, and so yeah.
That was something that from this conference I really got was excited thinking about the fact that you can actually tell something about the kind of gas that's inflowing or outflowing just by looking at sort of what in situ now the gas metallicity is, because the really low metallicity has a completely different origin than you would get from recycled outflows.
I don't know how you can draw it there, but yeah.
Matilde wants metals in the outflow.
Let's see. I know people are now like looking at me like, how is Katie going to do this? I could, I think.
And I think metals are driven out to the CGM scale as well, right? So maybe it's something to be on the left.
Yes, that's where I'm going to put it. I might just cheat and put like CO, iron. Let's just pick some metals we like. Astronomers I know make geologists very upset when we talk about metals. Yeah, nitrogen, yes.
Also somehow all the way to the CGM.
I'm gonna say, just based on my own skill in being able to continue to add to this plot, why don't we're at 10 minutes over the discussion section time for us anyway. I know Matilda and Darshan have closing remarks. So I had one more thing I wanted to draw. So the last thing I was going to say is, I don't know about you, but this has been an incredible conference, and I think that we need to give a huge amount of credit and applause to Darshan and to Matilda for making this so engaging and interesting and fun. So thank you both so much. And with that, the discussion section is over. Don't you worry, this will be available online. I will sign it in case anyone needs an autograph for the beautiful art. And thanks again for making this discussion section so fun.
Thank you, Katie.
Thank you, Katie, because this was really like a great overview of the week, I think. So thank you very much. And we will just we will be very, very brief at this point because we are definitely late on the schedule. Wait, where are our slides? Just a second.
We can just share the browser.
Yeah, Firefox.
Okay.
Wait, I have to. Where are they? Closing remarks. Yes. So. Well, first of all, definitely we had we had a very long title for this conference because we couldn't figure it out. Another way to link all the things that we wanted to discuss during this week. We have to say that in the end it was a very ambitious. It was ambitious to try to fit all the topics that we wanted to that we discussed this week in just 4 days and a half.
Exactly. So you guys were working on this for like tens of years, which you summarized in about 10 or 20 minutes or so, and we were trying to summarize that in like about 10 minutes. So
like
it was definitely ambitious more.
Yeah. And what we wanted also to have this week was to have like an overview of the most recent results from observations using different instruments, so JWST for sure, but also other state-of-the-art instruments that are very important to complement JWST discoveries and also ideas for future instruments. So it's great that we have discussed a lot about HWO and what the future is and what the future is giving us, is about to give us, and also to discuss theory and simulations to understand how to interpret these results. So we hope that you had a lot of food for thoughts and that you had like there were multiple occasions in the end to socialize and we hope that this kind of occasion can give was useful to gather new ideas for the future. And we had for each session, we had many questions in mind, but then we had to write something to put in the website, and so we wanted a shorter version of that. So these are the questions that were in the website for the first session that we had on Monday and Tuesday. I don't think that we actually discussed completely these three points because they are pretty like they span a very broad range of topics. But definitely now we have more questions than before, and I was trying to think about about it in like yesterday evening actually, and I gathered some of the open questions, some of the things that we discussed, and probably there are even more, and I don't want to, I mean, I don't think that we have even the time to go here and discuss point per point, but this is true for all the other sessions of this conference. I don't know if Darshan you want to be more specific about some of these points, or
I think the last discussion session covered pretty much like what we wanted to cover from the entire conference itself. So I don't think we'll go through this point by point. We just quickly put up a brief summary of what was happening, but I think that was already covered just now. So yeah.
What we can do is that we will upload these on Slack, and we hope that we can go on discussing it there or in at lunch now, and also in the future.
So hopefully you've had some food for thought for what we're going to do over the next week, months, years, 30 years or so. Hopefully habitable worlds will come true soon, maybe in 10 years or so. So thank you so much. We really appreciate you joining us for this conference. We've had a wonderful time. It's the first time that we've had this major Galaxy Evolution conference in like many years now at the Institute. But then before we leave, we would really like to thank the EPG, the Events and Plannings Group at STSCI for making this happen. There is a lot of effort that has gone in the background, from like hotel bookings, from the logistics, from like, the power shutdowns and everything like that. So Sherita and Shamaya, we really appreciate all the efforts that have gone into this.
Thank you very much. And then, of course, all the support that we got also from Thomas, Gary, and Kevin, who helped to set up the room every day and the e-posters in the cafeteria. So also let's thank them, right back there. So let's thank them. And of course, the SOC and LOC, again, that helped a lot for the SOC for the selections of the abstract, the LOC for all the logistics organizations during this week and also in the previous weeks. So Thank you very much.
Socialization-wise, LOC really gave us a lot of ideas. The beer thing, the baseball thing, and everything like that. We can only go as far, but the LOC really helped us, like making this more interactive, making sure that the posters are also visible. Like this thing has been done for the first time in SGSA. Hopefully this worked, but then yeah,
hopefully it worked.
Okay, yeah. So thank you so much, and enjoy the lunch.
And come back at 1 p.m. for the workshop.
Yeah, same place, yeah. Thank you.
Thank you.